Good morning, I am Seema from BSc Chemistry Honors Final Year. This video is specially for the visually impaired students. Let's start the chapter Physical Properties and Molecular Structure. Introduction. The various methods used for the study of molecular structure may be broadly classified into the following two types. Method based upon the study of physical properties of the substances such as molar refraction, optical activity, magnetic susceptibility, Paraker based upon surface tension, dipole moment. Spectroscopic methods such as rotational and vibrational spectroscopy, microwave and infrared spectroscopy, electronic spectroscopy, UV and visible spectroscopy, Raman spectroscopy, nuclear magnetic resonance, NMR spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property the total volume of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as that property which depends upon the constituents of the molecule, that is arrangements of the atoms within the molecule and the presence of the multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed in chapter 3rd. Now in this chapter we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment and magnetic susceptibility, one by one. Optical activity. Definitions. Plane polarized light. If a ray of light travels in any direction, it has vibrations in all the directions at right angle to the path of propagation. If this light is passed through nickel prism, then a nickel prism devised by the scientist Nicol consists of two prisms joined together. Each of these prisms is made up of a substance called eclat, spar or calcinate, which is mainly calcium carbonate. If a single prism is used, it is found that two beams of light come out, each of which is plane polarized and the planes of two are at right angles to each other. By combining with second prism, one of beams undergoes total internal reflections and only one plane polarized beam becomes out. Instead of nickel prism, a Polaroid is also sometimes used. It consists of a film of cellulose acetate mounted between two glass plates, which emerges out of the prism is found to have vibrations only in one plane. This light is called plane polarized light. The nickel prism thus used is called polarizer. Optical activity. If the plane polarized light is passing through a plate of quartz or turpentine oil or the solution of sugar taken in a glass tube, it is found that in the light that comes out, the plane of the polarized light gets rotated. The substances like quartz, sugar, etc., which rotate the plane of polarized light are called optical activity substances, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane of polarized light to the right are called dextrorotatory, and those which rotate the plane of polarized light to the left are called levorotatory. The method of observing the rotations of the plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another nickel prism which has its axis parallel to the of the first nickel prism, the light passes through and brightness is observed through the eyepiece. On the other hand, if the second nickel prism is placed with its axis at the right angle to that of the prism called crossed position, the light is completely cut off and field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if the two nickel prisms are set at the crossed position so that the field of view is completely dark, and then the optically active substance is placed between the two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through a certain angle about the line of propagation of the light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. The degree of rotation depends upon the rotations required to be given to the second nickel prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. The next is the specific rotation. The angle in degrees through the which the plane of polarized light is rotated on passing through the solution of an optically active substance depending upon the following factors: nature of the optically active substances, construction of the solution, length of the solution, that is the length of the tube through which the light passes, wavelength of the light used, temperature of the solution. Thus, if micrograms of the substance are dissolved in V ml of the solution, so that the concentration of the solution is mV per milligram. L is the length of the tube and alpha is the angle of rotation in the degrees. Then it found that alpha is directly proportional to concentrations multiply length of the cube in dm. Alpha is directly proportional to m by v into L. Alpha is equal to m alpha by half m into Lv, where it is a constant characteristic of the nature of the substance and depends upon the wavelength of the light used and the temperature of the solution. If D line of the sodium vapor lamp is used and the temperature of the solution is 25 degrees Celsius, then it is written as this constant is called specific rotation of the substance. Thus, from the above equations, hence the specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 the solution, and the length of the solutions through which light is passes is 1 dm. If all reported values of the concentration of solution is taken in the graph upon 100 ml of the solution, this if C grams are dissolved in the 100 ml of the solution, then we may put m is equal to C and v is equal to 100. This gives further, if instead of a solution substance taken in a pure liquid or solid, then m upon v is replaced by density d of the pure substance. In case of pure solid, L is taken as thickness of the solid in dm. Molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight of the substance and dividing the result by 100 to reduce the magnitude of the number. It is represented by m into t lambda. Thus, the measurement of optical activity, that is angle of rotations, that is alpha. The instrument used for the measurement of the amount of rotation in degree caused by an optical active substance to the plane of the polarized light, it is called a polarimeter. The principle of this instrument has already been discussed. It consists essentially of two nickel prisms called the polarizer and the other called the analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of tube. In between the polarizer and the analyzer, there is space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm, or 25 cm and has glass windows as both ends. A circular scale is fixed on the metal tube near the analyzers. In the procedure, first of all, monochromatic light is from a suitable source, usually sodium vapor lamp, is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of the view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution is placed and the shutter closed. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of the view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation. If it is comes out to be positive, the substance is dextro-rotatory, and if negative, it is levo-rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same: optical activity and chemical constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of the atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or groups are attached. Such a carbon atom is called asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid, as represented below. Quite often, the instrument is used for finding the concentration of the sugar solution from a measured value of alpha and known value of alpha, and using the formula the instrument thus used is called saccharimeter. It is found that such a compound exists in two forms, one of which rotates the plane of the polarized light to be right and is called dextrorotatory, and the other which rotates the plane of the polarized light to left, it is called levorotatory. The two forms have the same constitutions, that is, each forms asymmetric carbon atom is attached to the same four atoms or groups but differ in the configurations. Thus, the two forms are space isomers called the optical isomers. Lee, Bell, and Van Hoff pointed out the difference in the two forms by suggesting that in such of molecules, the asymmetric carbon atom is present in the center of the regular tetrahedron, and the four atoms of groups atoms to it are present at the corners of the tetrahedron. This gives rise to different spatial arrangements which were like the mirror image of each other. The two above two configurations are different in sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. The above two forms may be represented in the form first, the arrangement from H to OH is clockwise, and in form second, the arrangement of H to OH is anticlockwise. Hence, if one of them is dextrorotatory, the other is levorotatory. However, by mere inspections of the configurations, it is not possible to predict as to which form is dextro or levo. The two forms are said to be the enantiomorphous. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation caused by one form of the right is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is multiplied by equal rotation caused by the second form to the left. This process is called external compensation, and the substances thus obtained are called racemic mixtures. This form can be separated into D and L forms by suitable methods. In case of compounds containing two asymmetric carbon atoms, a fourth form is called formed to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule. This form, which is optically inactive due to the internal compensation, is called mesoform. Lastly, it may be mentioned that optical activity is not found only in the organic compounds containing as asymmetric carbon atom but also in the compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atoms but are optically active. Because the molecules as a whole is asymmetric, no plane can be divided the molecule into two identical halves. Thus, it may be concluded that the optical activity is a property related with asymmetry of the molecules. Hence, optical activity can be used to test the presence of asymmetry in the molecule. Dipole moment. General introduction. Polar and non-polar covalent bonds. A covalent bond is formed by the mutual sharing of electrons between the two atoms. If the two atoms are identical, example H2, Cl2, etc., the shared pair of electrons is attracted equally by both the atoms and hence it remains exactly in the center of two atoms as shown below. HH exactly in the centers, CL exactly in the center. Thus, neither of the two atoms in such molecules acquires positive or negative charge. Thus, the bonds formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in HCl molecule, chlorine atom is more electronegative than the hydrogen atom. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electrons is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine end of molecule acquires a slight negative charge while the hydrogen end of the molecule acquires a slight positive charge. The bond thus formed between the two atoms, two dissimilar atoms having slightly different electronegativities, is called polar covalent bond and the molecule is called dipole because it has develop positive and negative poles. Thus, the situation in HCl may be represented as dipole moment of a diatomic molecule. The extent of polarity or polarization of a molecule is the molecule and the average is expressed in terms of dipole moment. which defines as follows. The dipole moment of a polar diatomic molecule is the product of charge on each end of the molecule and the average distance between the centers of their nuclei, that is bond length. In general, for a polar diatomic molecule AB in which the atom B is more electronegative than the A, if positive Q is the charge on the end A and negative Q on the end P of the molecule and D is the average distance between the centers of their nuclei, then the dipole moment of the molecule AB is given by mu is equal to K into D. Obviously, if the molecule is nonpolar, K is equal to 0 and hence mu is equal to 0. Units of dipole moment. The charge present on the ends of the molecule is usually of the order of the 10 into raised to the power minus 10 ASU, and the distance between the atoms, that is bond length, is usually of the order of 10 to the power minus 8 centimeter, that is angstrom units. Therefore, mu must be the order of 10 raised to the power minus 10 into 10 raised to the power minus 8 is equal to 10 raised to the power minus 18 ESU centimeter. This value is called 1 dBi after the name of the pioneer worker in this field. Thus, 1 dBi is equal to 10 raised to the power minus 18 ESU centimeter. Vector nature of the dipole moment. The dipole moment is a vector quantity, hence it has both electrons towards itself. The average value is taken because atoms keeps on vibrating with respect to each other. In the diatomic molecule, the positive charge on one end of the molecule must be equal to negative charge on the other end because the molecule on the whole is electrically neutral. Magnitude as well as the direction. It is therefore represented by an arrow pointing from positive end to the negative end of the molecule. Dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than the two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the directions of the bonds. Thus, if a molecule AB2 contains two A to B bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of the molecule will be mu is equal to 2 mu AB cos theta by 2. As mu is known from experiments, therefore, knowing the value of theta, the methods is usually used for the calculation of bond moments. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence for predicting the shapes of the molecules. The experimentally observed value of the dipole moment of some common molecules and the calculated value of bond moments of some common bonds are given as electrical polarization of the molecules. Every molecule is made up of the positively charged nuclei and negatively charged electrons clouds. The center of positive charge coincides with the center of negative charge. Hence, when such a molecule is introduced between two plates of an electric field, the positively charged nuclei and hence the center of positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positive plate of the electron field. As a result, the molecule gets distorted. This is called polarization of the molecule, and the distorted molecule with positive and negative ends is called an electric dipole. The molecule remains polarized so long as the electric field is applied but goes back to the original state as soon as the electric field is switched off. This is why this type of polarization is called induced polarization, and electric dipole form is called induced dipoles. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to negative charge on the other. Suppose this charge is Q. If D is the distance of separations between the charge, then the dipole of the induced dipole, called the induced dipole moment, represented by mu, will be given by mu I is equal to K into D. Evidently, the value of mu I will depend upon the nature of the molecule and the strength of the electric field. Say X, we write mu I is equal to alpha into X, where alpha is constant and is called polarizability of the given molecule. Alpha is further found to be related to the dielectric constant d of the medium present between the plates, that is molecules being studied according to the equations put forward by Clausius and Moissanti, where m is the molecular mass of the molecules, rho is the density of the molecules, n is the Avogadro's number. Clausius-Moissanti equations suppose an electrostatic field is applied to two plates so that they are changed Suppose the strength of the uniform electric field produced between them is equal to mu naught. Now, if a non-polar medium is placed between the plates, the strength of the electric field will be reduced to E because the induced dipole called dielectrics act in the opposition to the applied field and hence partially neutralize the charge of the plates. The ratio E naught by E is called the dielectric constant d relative permittivity of the medium. From electrostatics, it can be shown that mu naught is equal to E plus 4 pi I, where I is the induced dipole moment per unit volume. I is equal to mu I into n, where mu I is induced dipole moment is a single molecule and n is the number of the molecules per cubic centimeter. Dividing both sides of equation 4th by E and putting E naught into E is equal to D, then we get the relations, that is D is equal to 1 plus 4 pi I upon E. The intensity of the electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plates. The electric intensity X is then made up of the following parts. That is, first is the field strength of the changes on the plates E naught. The charges induced on the surfaces of the dielectrics in contact with the plates is equal to minus 4 pi I. The charge induced on the surface of the spherical cavity is plus 4 by 3 pi I. The next is, as all the quantities on the right hand side of the equation 12 are constant, alpha being constant for a given substance independent of temperature, therefore the quantity on the left hand side of equation 12 must also be constant independent of the temperature and depending only upon the nature of the molecule. This quantity is called molar polarization and is represented by P. Further, as applied field produces an induced charge in the molecule by the relative displacement or distortion of the electrons and nuclei, P is often called induced or distortion polarizations and is represented by Pi or Pd. Thus, induced molar polarization is defined as the amount of polarization produced in the 1 mole of the substance when placed between the plates of an electric field of unit strength. From equation 13, it is evident that the units of Pi will be same as those of a molar volume. Hence, Pi is usually expressed in centimeter cubic per mole. Expression 13 gives the relationship between dielectric constant and polarizability was first derived by Mosati and Clausius and is called Mosty-Clausius equation. Effect of temperature on polarization. The values of molar polarization have been determined for a number of the substances. It is found that whereas molar polarization of the number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization values for some other substances such as HCl, CHCl3, C6H5NO2 and CH3Cl do not come out to be constant but decrease with increase of temperature. This observation has been the basis of the measurement of dipole moment and the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, their centers of positive and negative charges do not coincide with each other. Thus, they possess some dipole moment even in the absence of the electric field. The dipole moment thus possessed by the molecules is called permanent dipole moment. In the absence of electric field, these permanent dipoles are oriented in a random manner due to thermal excitations. However, in the presence of electric field, the two disturbing effects takes place. These are the electric field will tend to rotate and orient these dipoles in the direction of the field. The electric field will tend to polarize the molecules. If the molecules were stationary, the dipoles would have been oriented perfectly parallel to the electric field, that is at the right angles to the plate of the electric field. However, due to thermal excitation, they take up position in between that of original state and the perfectly parallel states. Thus, in case of the molecules possessing permanent dipoles, the right hand side of equation 13 will give total polarizations, which will be the sum of induced molar polarization and the orientation molar polarizations. Measurement of dipole moment. First is vapor temperature method. The above equation can be written in the form of Pt is equal to A plus V by T. A is equal to 4 by 3 pi n alpha and B is equal to 4 pi n mu square upon 9 k. are constant for the given substance. This equation is primarily applicable to gases and vapors. Thus, if Pt is plotted against 1 by T, a straight line graph will be obtained if the molecules possess permanent dipoles. The slope of the plot will given by B is equal to 4 pi n mu square upon 9k. From this equation, the permanent dipole moment of the molecules can be calculated as all other quantities are constant whose values are known. The straight line plots for a few substances with the and without the permanent dipole, polar and non-polar molecules. It may be seen that the whereas Pt varies with temperature for HCl, CH3Cl possessing permanent dipole, there is no effect of temperature on the substances like CH4, CCl4, etc., which do not have permanent dipoles and hence possess only induced molar polarizations. Methods of measurements of dipole moment. As explained above, the basic equations for the determinations of the dipole moment is Pt is equal to d minus 1 into d plus 2 m upon rho is equal to a plus b upon t. A and b are constant with b is equal to 4 pi n mu square into 9k. Thus, the experiment involves the determination of the dielectric constant d and the density rho at the different temperatures T. The value of Pt are then calculated and plotted against 1 by T. If Pt is found to have vary linearly with 1 by T, the substance possesses a permanent dipole moment and the value of the dipole moment is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment, that is nonpolar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plates and then measuring the capacity of the same condenser when filled with the given substance. The dielectric constant of the given substance is then given by D is equal to C upon C naught. Refraction method. According to Clausius-Most equations, the induced or distortion molar polarization PD of the molecules is given by PD is equal to D minus 1 upon D plus 2 into m upon rho is equal to 4 by 3 pi n. As the dielectric constant is a pure number, molar polarizations P is simply molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell that the dielectric constant of the substance is related to its refractive index for light of the long wavelength according to the equations. However, n square infinity cannot be found by extrapolation to infinite wavelength. The values of refractive index is measured with visible light. This is because visible light can be displaced only electrons, whereas the positively charged nuclei remains unaffected. Thus, the distortion polarization can be considered to be the sum of the electron polarizations and atom polarizations. The polarizability alpha is also accordingly made up of the two parts alpha E and alpha A called electron polarizability and atomic or nuclear polarizability. To find the total value of the PD, it is therefore necessary to measure the refractive index using the infrared rays because they can displace the heavy atomic nuclei as well as electrons. But measurement of refractive index with infrared radiations is difficult. Hence, the problem is solved by finding the electron polarization by measuring the refractive index using visible light. As approximation 50% of these values is added to it account for PA to get the total value of PD. And then, as before, total polarization of a molecule possessing a permanent dipole moment is the sum of the two terms, the first called the distortion polarizations and the second called the orientation polarization due to permanent moment possessed by the molecules. Hence, we write Pt is equal to Pd plus P naught. Pt can be determined by finding the dielectric constant of the vapor at the temperature T, and Pd can be found either by measuring the refractive index using infrared radiations or by approximations method explained above. This method is similar than the temperature method because it involves the measurement only at one temperature. Dilute solution method is applicable to the gases and vapors only. For substances which are not gases or which cannot be converted into vapors, the following procedures is followed. A dilute solution of the given substance is prepared in a non-polar solvent such as the benzene, CCl4, CS2, etc. The density and dielectric constant of the solution are determined at the various temperature. At each temperature, the molar polarization of the solution PS is calculated using the relation where X1 and the mole fractions of the solvent and the solute in the solution. M1 and M2 are their respective molecular masses and ρ is the density of the solution. The molar polarization of the solution is related to the molar polarization of the solvent and that of the solute X2. Thus, knowing the value of the X1, X2 and P1 of the value of the P2 is that is molar polarization of the solute substance being studied can be calculated. To find total volume of PD, it is therefore necessary to measure the refractive index using infrared rays because they can displace the heavy atomic nuclei as well as electrons, but measurement of the refractive index with infrared radiations is difficult. Hence, the problem is solved by finding the electron polarization by measuring the refractive index using visible light. As an approximation, 5% of this value is added to it to account for a PA to get the total value of the PD. Then, as before, total polarization of a molecule possessing as a permanent dipole moment is the sum of the two terms, the first called the distortion polarization and the second called the orientation polarizations due to permanent moment possessed by the molecules. Hence, we can write Pt is equal to Pd plus P naught. Putting the value of P naught from Debye equations, we get mu is equal to 0.0128 into Pt minus Pdt whole root. Pt can be determined by finding the dielectric constant of the vapor at the temperature T and Pd. Dilute solutions method is applicable to the gases and vapors only. For substances which are not the gases or which cannot be converted into vapors, the following procedures is followed. A dilute solution of the given substance is prepared in a non-polar solvent such as benzene CCl4. The density and dielectric constant of the solution are determined at the various temperatures. The next is the dipole moment and the chemical constitutions. The knowledge of the dipole moment of a molecule can be applied in a number of the ways to study its chemical constitutions. A few important applications of the dipole moment are briefly discussed. First is in comparison the relative polarities of the molecule. For example, the dipole moment of the HF, HCl, HBr, HI are 2.0, 1.03, 0.78 and 0.38 dBi respectively. This shows that the polar factor of the molecule decreases as we move from HF to HI. In the calculation, the percentage ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 dBi. If the bond were 100% ionic each and would acquire the full 1 unit charge. The bond distance in HCl is taken to be 1.275 angstrom. Hence, if HCl were 100% ionic, the dipole moment would have been. In predicting the geometry or shapes of molecules, the fact that the dipole moment is a vector quantity and that a particular bond has almost a constant value of bond moment is very useful in predicting the shapes of the molecule. Few cases are described below. Diatomic molecule. A diatomic molecule is always linear irrespective of its dipole moment. Triatomic molecules. In triatomic molecules of the type AB2, there are two possibilities. The dipole moment of the molecule may be zero, that is in case of CO2 and CS2. This shows that in these molecules, one bond moment is equal and opposite to other. Hence, the molecules may be linear. The molecule may have a definite value of the dipole moment. Obviously, in this case, the possibility of linear shapes is ruled out. The two bonds must have a definite angle between them which can be calculated if we know the bond moment discussed earlier in sections. For example, the bond moment for HO is the bond angle is calculated to be nearly 105 degree angstrom. This H2O may be represented as such molecules are called bent molecule and the shape is called B shape. Tetraatomic molecule. In tetraatomic molecules of the type AB3, the two simple possibilities are the dipole moment of the molecule may be zero. In such a case, all the four atoms must be in one plane and the angles between the two bonds must be equal. Example in BF3. Such a shape is called planar trigonal shape. The molecules may have some definite value of dipoles. This indicates that the one atom lies out of the plane of the rest of atoms. For example, the molecules of ammonia may be represented as such a shape is called pyramidal shape. Pentaatomic molecules. The pentaatomic molecules of the type AB4, which may commonly common across RCH4, CCl4, SiCl4 and SnCl4. The dipole moment of all these molecules is found to be zero. This is possible only if these molecules have symmetrical or regular geometry so that the different bonds moments cancel out each other. The experimental facts confirms that these molecules have tetrahedral shapes. In differentiating the cis and trans isomers, the cis and trans isomers are represented as the second possibility is that the atoms may be in one plane but the angles between the bonds may not be equal. Then the plane is planar but not the trigonal. It is clear that the transform will be non-polar, that is will have zero dipole moment, whereas cis form will be polar, will have definite dipole moment. For example, in case of dichloroethylene putting HCl, cis form have been found to have a dipole moment of 1.9 dBi, while the trans form is found to have zero dipole moment. In differentiating the ortho, meta and para isomers, a benzene is a regular hexagon and its dipole moment is zero. Therefore, substituting two atoms or groups in the ortho, meta or para positions, the di-substituted derivatives will have different dipole moment for ortho, meta, para isomers. Obviously, para will have zero dipole moment and meta will have less dipole moment than ortho. In supporting the possibilities of resonating structures, for example, the nitrous oxide molecules has a small value of dipole moment. If the molecule is supposed to have any one of the following two structures, the dipole moment should be high. This confirms that N2O molecule is a resonance hybrid of the structures. First and second, measurement of magnetic susceptibility Gauss method. The magnetic susceptibility are generally determined by the method put forward by Gauss in 1889. It is shown that, briefly explained below, the material under examination is taken, a thin cylinder or a tube, which is then suspended vertically with a wire from one arm of the balance between the two poles of electromagnetic such that the lower end of the cylinder is nearly in the middle of the poles of electromagnetic. The cylinder is now counterbalanced in this position by placing weights in other plane of the balance. The current is now switched on into the electromagnetic. If the substance is paramagnetic, the cylinder will pull down so that the more the magnetic lines of the force can pass through it. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward so that the less magnetic lines of the force may pass through it. In the first case, some extra weights will have to be added. In the magnetic lines of force may pass through it. In the first case, some extra weights will have be added in the pen, whereas in the second case, some weights have to be removed from pen to restore the balance. Since the change in the weight is equal to magnetic force acting on the material, hence if delta m is change in the mass, where g is the acceleration due to gravity, so that delta mg is equal to 1 by half susceptibility minus susceptibility A into AH square. Delta mg gives the change in the weight. The right hand side is the magnetic force acting on the material of volume susceptibility, where A is the area of cross section of the specimen, H is the field strength, and XA is the volume susceptibility of the air. The next is in the above calculations, the absolute value of the field strength H is also required. However, the necessity of measuring H and A can be eliminated if the experiment is first performed with the substance of non-susceptibility using the same magnetic field and same cylinder of taking the substance. Usually, water is taken as the standard substance for this purpose. Thus, evidently, where delta ms is the change in the mass when the sample under examination is placed in the magnetic field, and delta mw is the change in the mass when water is taken in the same cylinder and placed in the same magnetic field. Magnetic susceptibility of the sample and X are those of water and air respectively. Magnetic susceptibility and the molecular structure. A detailed study of magnetic susceptibilities of a large number of organic and inorganic compounds has revealed that, like many other physical properties such as molar refraction, Paraker, etc. The molar magnetic susceptibility is an additive as well as constitutive property. These values assigned to the various atoms and to the structural factors, that is double triple bond rings, can be obtained from the experimentally determined value for a large number of elements and compounds. The values of the magnetic susceptibility for some of the atoms and structural groups are given below. That Experim- explanations of diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion, as they are charged particles. Therefore, their motion produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of the electrons spinning in one direction is cancelled by the magnetic moment of the electrons spinning in the opposite direction. The net result is that the substance has zero magnetic moment. If such a substance is placed in a magnetic field, small magnetic moment is induced in the substance in the opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of the behavior is observed for the diamagnetic substance. Thus, diamagnetism is exhibited by those substances which contain the paired electrons only, that is, no unpaired electron is present. On the other hand, if the substance contains some unpaired electrons, the magnetic moment of the electrons do not cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electrons behave like a micromagnetic with a defined magnetic moment. If such a substance is placed in an external magnetic field, the micromagnets will arrange themselves parallel to the external field, and the induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substance. Substances are therefore attracted by the magnetic field instead of being repelled by it. This type of the behavior is observed for the paramagnetic substances. Thus, paramagnetism is exhibited by those substances which contain some unpaired electrons. Determination of magnetic moment for a paramagnetic substance. As explained above, each atom, ion, or molecule of a paramagnetic substance behave like a micromagnet with a definite inherent magnetic moment of magnitude μm. Then such a substance is placed in the external magnetic field, the micromagnets tend to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particles, because magnetic susceptibility of the paramagnetic substances varies with the temperature. Hence, the actual arrangements taken up will depend upon the temperatures. Lagrange in 1905 put forward the following relationship between the molar magnetic susceptibility, magnetic moment, and temperature. X of m is equal to xm into mu square m n upon 3 kt, where n is the Avogadro's number, k is the Boltzmann constant, and alpha m is a constant for the given substance. It represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. In equation 11, all the quantities are constant except susceptibility m and t. Thus, determine the susceptibility for the given substance, a different temperature T, and then plotting susceptibility Vs temperature. A straight line graph will be obtained, the slope which will be equal to the mu square m n upon 3k, where mu m can be the calculated relationship between the magnetic moment and the number of the unpaired electrons. The total magnetic moment of any atom or ion or molecule is the sum of the following two values. Magnetic moment due to the orbital motions of the electron, it is equals to square under root L into L plus 1 Bm, where L is azimuthal or orbital quantum number for that electron. Magnetic moment due to the spin motion of the electron, it is equals to the 2 into on root s into s plus 1 bm, where s is spin quantum number having value equal to 1 by half. If ions or molecules are considered instead of free atoms, it is expected that the orbital motions of the electrons are tied into the nuclear configurations of the molecule or the ion so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution due to the orbital motion is negligible. Thus, the magnetic moment of the molecule or the ion is mainly due to the spin motion of the electrons. Hence, it is called spin magnetic moment. Here, S represents spin quantum numbers for one unpaired electron for a molecule or ion containing a number of the unpaired electrons. The expression is usually written as mu is equal to 2 under root s into s plus 1 bm, where capital S represents the total spin quantum number. Thus, for no unpaired electron, S is equal to 1. S is equal to half 1 by 2. Thank you.